All right. One. All right. Hi, everyone. Hello. Quiet down, please. Hi. So, okay. All right. So what I want to do today is, again, kind of do a derivation of a slightly more complex example of analyzing for complexity. And we'll do it from scratch because there was kind of some noise last time at the end. So just very quickly, so the idea was bubble sort, and the idea was basically if you have a list, so basically if you have a list that's like this, then what you can do is you can just repeatedly go and compare neighbors and swap them if necessary. So here 5 and 10 do not need to be swapped, and then 10 and 2 are out of order, so you do swap them. And then 10 and -2 are out of order, so you swap them. And then 10 and 20 are not out of order. And then you do this again. So you say, are 5 and 2 out of order? Yes. So that's going to be like this. And then are 5 and -2 out of order? Yes. So that's like this. And then are 5 and 10 out of order? No. 10 and 20 out of order? No. And then you do it again. So now it's going to be -2, 2, and so on. So that's the basic process. And then I'll just repeat quickly what the code was like. So what we want to do is we want to say for I in range. So in the first place, I'll say length of L -1. And the idea here is I just want to go through the input list and swap as necessary. So that would be one pass through the list. So I'll just say if they're out of order. So if L at I plus 1 is greater than L at I, then I swap. So L at I plus 1 is L at I plus 1, L at I. And then the next idea is, well, we'll do it repeatedly. So I'll say for J in range length of L, I'll just keep doing this. And that already works. And now we can have several improvements. So one of the improvements was, well, you don't actually need to go up until the end of the list every time. And that's because after just one pass, so after you execute this just once, the maximum element is already at the end of the list. And that's because if it's the maximum element, it'll get swapped repeatedly until it gets to the end. So what we'll say is when J is equal to 0, we'll do it up until length of L -1. Length of L -1, by the way, because you want to compare the second to last element to the last element, but you cannot compare the last element to the one that comes after that. There's no element after that. And then the second time, it's going to be -1 so that you don't make this last comparison, because you don't need to, because the last element is already definitely in its correct place. So that's one improvement. And then the other improvement is if you go through all of that and you never make a swap, there is no point in trying again because you already went through the list and you never made the swap. That means the list is sorted. So we introduce this variable swap, which we'll set to false before we begin this. And then anytime we make a swap, we say swapped is true. And then over here, we'll say, well, if swapped was not set to true at any point, then we're done. So I'll say if not swapped, then return. That's it. So this function doesn't really return anything in particular. So by default, it returns none. And that's because its job is to modify the contents of L rather than to create a new list, right? So that was the distinction between doing L.sort, so that's modify the contents of L, and doing like L1 is equal to sorted of L, which actually doesn't change L, but creates a new version that's sorted and stores it in L1. So, okay. So now last time we kind of did operations in a quite detailed way. So this time I'll do the same kind of computation, but just eyeballing it more, and both ways are legitimate, right? So what am I doing here? I'm saying, okay, basically the runtime of this entire thing is going to be proportional to the number of times that this block of code is executed. Why is that? Well, because that's the innermost thing that happens inside the nested loop. So that's the thing that gets repeated the most times. And nothing else seems to be taking that much time. In fact, you could make it, and we made the mathematical argument last time, right? So you can make it more precise by saying, well, like, sure, like you need to take some time to perform just this, like make j be 0 and then 1 and then length of L minus 1. But that's going to take strictly less time than it's going to take to do this repeatedly, because this repeats multiple times for every time that j is incremented, right? So this gets repeated length of L minus 1 minus j times for every increment of j. So that means that incrementing j, so the time that the code would take to set j to 0 and then 1 and so on, is going to be much, much less than the time that it's going to take to just repeat this. And then there's also going to be some time that's taken to make I be 0 and then 1, then 2, and so on, up to length of L minus 1 minus j. But the amount of time that this line takes is going to be proportional to the amount of time that this block takes, because they both, like every time you increment I, this block gets repeated, right? So the argument is, don't really need to count how much that time that takes, because what this one takes is just proportional to what this one takes. So might as well just count one of them. And then don't really need to count this, because the amount of time that this takes is like a lot less than the amount of time that it takes to do this repeatedly. In fact, how much less? Well, for every time that j is incremented, you repeat the innermost block this many times. So more than one. So, okay. So how many times does this get repeated? So here, like, it's kind of difficult to count because it's not a multiplication. You cannot multiply length of L but by length of L minus 1 minus j, because j keeps changing. So what you need to do is you need to add it up, right? So how do you add it up? Well, the first time that it gets repeated length of L minus 1 times. And then the second time that it gets repeated, it's length of L minus 2. And then the third time, it's length of L minus 3. And so on, up to length of L minus length of L, right? At this point, it's just 0. So now we just need to compute this. So one way to do it is to do it, again, I'm trying to do it a different way than last time, just for variety. So what I'll do is I'll just invert it. So this is 0. And then the second to last term would be 1, and then 2, and so on. So this would just be 1 plus 2 plus 3 plus length of L minus 1. And now we just need to compute this. So again, the formula that you definitely need to know is 1 plus 2 and so on plus k is equal to k times k plus 1 over 2. So here what we'll do is we'll substitute k is equal to length of L minus 1 into the formula. So this would be length of L times length of L minus 1 over 2, which would be half length of L squared minus half length of L. And this is O of length of L squared. Great. So that's the same result as last time. Last time, remember, it was also length of L squared over 2. And that's exactly what we got. And the kind of the lower order terms don't matter, right? So what matters is the component here that grows as fast as possible. Because for large length of L squared is going to be much, much larger than length of L. So that means that we just care about this. And the constant proportionality, the 0.5, again, doesn't matter because we care about what's the runtime proportional to. So the number of times that this block gets repeated is proportional to the runtime on any particular device. And that's going to be proportional to length of L squared. Right. So what we had so far was counting sort, which was O of length of L plus max of L. And we now have bubble sort, which is O of length of L squared. We'll have so bubble sort is like well, like not the most efficient thing. It's just kind of good for example's sake. So we'll also have, if we have time this semester, for merge sort, which is, it's a little bit complicated, but basically O of length of L log length of L. And here, so you could imagine that max of L is very large because L contains a very, very large integer, so that counting sort would not be feasible. This is usually, or this or something like this is usually what you want to do. And this is basically Python sort. So this we'll do hopefully next week or the week after. We will now do something that's like even less practical than bubble sort, just to see kind of like the variety of analysis that you could have. So one more thing to note here is here the worst case analysis is actually important. And that's because the worst case here differs from the best case. In the best case, the list is already sorted. And if the list is already sorted, then swapped is just always going to be false. And after you do one pass through the list, you're going to be done. So one pass through the list means that you just execute this block of code the once, and that's going to be proportional to length of L. So technically, if you think about what's the worst case here, you might imagine that by some kind of weird math thing, it's always going to be the case that swapped becomes true before you think it would, right? You might like it's not the case, but you might imagine the situation where, well, like you can just mathematically prove that after 3 iterations of this, you would definitely always be done. So that's not the case. And the reason it's not the case is you can just say, well, imagine that what happens is you have a list like that, and it ends with -40. So the -40 can only travel one place during the one pass, right? Because you swap like everything here, everything here, everything here. And at the end, minus 40 gets swapped with 20 the once. And then you do a whole new pass. And again, minus 40 can travel back one place. So how many iterations do you need in order to get minus 40 back to where it belongs, which is at element number 0? Well, n minus 1. All right. So yeah. Well, I mean, why exactly is like because of this. So it's not like I can't give you a one sentence answer. Because I did this calculation, right? So I was trying to say, okay, like when I'm counting how many times this gets repeated, I said when j was equal to 0, this repeats length of L minus 1 times. And then when j is equal to 1, this repeats length of L minus 2 times, and so on. And then I added up all the times that this block got repeated. And it that the formula for how many times this gets repeated is length of L squared over 2 minus length of L over 2. And that's of length of L squared. So, okay, other questions? All right. So that's that. And with the worst case, it's generally okay to kind of be a little bit loose with it and say, well, I mean, in the worst case, swap never becomes true. In the worst case, it always becomes true, rather. Sometimes it's going to get more complicated. So here, as it turns out, that was a fine assumption. So, okay. So that's like that. So I want to do one more sort. And so this is called, so sometimes people make the distinction between Bozo sort and Bogo sort. So this one is called Bogo sort. And the idea is like this. So I start with a list. If it's sorted, we're done. If not, swap two elements. Check if it's sorted now. If yes, then you're done. If not, well, just try again. So let's do that. So we'll go sort. So what I need basically is two random elements here. It needs to be different elements every time, right? So I'll say like ij is random.random, random.random. Beta of 3, you're too loud. So, okay. And now we'll swap them. But only if we need to. So I'll say if not, so if is sorted L, we'll return. And otherwise we'll swap. So if sorted, I still need to write. So I'll just say swap L at I and L at J. So let's not generate those if we don't need them. So that's going to be like this. So now I need to write the function as sorted. So it would be kind of unsporting if I just used sorted inside here. I could, right? So I could say return L is equal to sorted of L. That would definitely work, right? So like if L is the same as the sorted version, then it's sorted. If not, then not. So that's that would do it. Of course, like if I have sorted the built-in Python function, why am I writing bogus sort to begin with? So I'll write my is sorted. That shouldn't be too difficult. It's the same as the midterm. So I'll just check, is Li plus 1 smaller than Li? And if it is, I'll return true. False rather. And here I'll return true. So, okay. So now I have is sorted, and that's bogus sort, right? So it's not a very efficient algorithm, but it does work. So if I do like 5 to 10 minus 5, whatever, and I say bogus sort L, and if I import random, and of course, here I need to actually make this random int. Let me make a random integer. So there is a built-in function for that actually, but I'll write my own. So this is something we've done already in the past, so I'm not going to. So here I'm just getting a random index, right? That did not work. So here, so this seems right. This seems right. Oh, I did not do a loop here. So here what I'm doing is I'll just keep doing this, and I said while true because I'll stop when I just say return. And here it is, it's sorted. However, if I add a couple more elements here, 3. At some point, I'll start noticing that it gets noticeably slower. Not yet. So now it's thinking. It will, I think, finish at some point, but not right away. And the reason while it's thinking about what the sorted version of this very long list is, we'll figure out the reason that it's quite slow. So one thing that you could see right away is, well, like technically it could be an infinite loop. So if you swap 2 elements and they're random elements, like there's no guarantee that the next pair of elements will just be the same element where you go back and forth swapping the same pair. So with that said, we can kind of informally estimate how long it's going to take. So in the worst case, the runtime is infinite. Because in the worst case, I and j are always the same. But we can kind of get an estimate for how long approximately this is going to take by saying, okay, so assuming kind of reasonably random, what we're going to do is we're going to cycle through every possible permutation of the list. So permutation is just a rearrangement until we find the sorted version. So we just need to know how many permutations there are of a list. So that's, again, kind of a result from math. A list of length n has n factorial permutations. So n factorial is 1 times 2 and so on times n. So on average, we'll go through O of n factorial permutations. Now, every iteration of the loop is not actually constant time, right? So every iteration of the loop requires that we run is sorted. Which is O of n. And here, of course, we're assuming that n is length of L. So that means that approximately the algorithm is O of n times n factorial, which is approximately O of n plus 1 factorial. So factorial grows extremely quickly, which is why this still hasn't finished running. So I think I'll put it out of its misery and make the list like slightly shorter so that it completes within a reasonable amount of time. So that's probably going to run for a while. So here, kind of the worst case analysis, strictly speaking, you would just say, well, it's extremely unlikely that you'll never return because you keep shuffling the list. Eventually, it should be sorted. But strictly speaking, in the worst case, it's an infinite loop. In the worst case, it just never sorted, so you never return. So it's an infinite loop. But on average, you can say, well, you're kind of going through all the permutations. There are n factorial of those. And you'll go through, well, like every one or like half of them or something. So that's approximately proportional to n factorial. And then every check for whether L is sorted takes time that's proportional to n. So in total, that's going to be n times n factorial, which is about the same as n plus 1 times n factorial, which is about n plus 1 factorial. Yeah. N factorial is not so n factorial is not proportional to n to the n, but it's like about that much. Yeah. So the thing about proportionality is like n plus 1 factorial is not proportional to n factorial. In fact, it's a factor of n plus 1. So like every small change there is gonna break the proportionality, but it's like about that. So okay, it's done. So here it's gonna be like that. So okay. So what we're going to do now is we're going to do one more thing. Sorry. Yes. Okay. Well, like if it's not not sorted, so Not sorted means that for some I, this is not, this is true, where they're out of order, right? So it's enough that the list is not sorted in one particular way for the entire thing to not be sorted. Oh, you mean like if it's sorted like in an increasing order as opposed to decreasing or something? Yeah, I mean, like that's a matter of a name, right? So here, like you got to be consistent about whether you want it to be sorted in increasing order or decreasing order. So here we mean increasing, technically non-decreasing. They meet this condition, but the rest of the elements in the list don't meet this condition. Well, yeah, I mean, like, so that would be kind of a situation that's like this, like, so like 1, 2, 3, and then like -1, then 5, 6, 7. Well, yeah, so that's not sorted. And then here you won't return false. And then here you won't return false. You'll just keep going. And then here you'll see that those ones are out of order, so you return false. And remember, once you return something, so once you get to this line, that's it, you've returned false. And that's exactly what you want, right? So you want, if any two neighbors are out of order, then you return false right away. If you go through the entire list and never return false, then you can say, well, I never returned false, so now I can return true. Yeah, but if it returns true, right, in if it's returning true, we are already well, we're not returning anything here. We're saying return. So what we're doing here is we're changing the contents of the list out, right? It's not like we're returning anything, and we're returning none, in fact. Yeah, but the end of so it wouldn't change anything else. Sorry, guys, I can't hear the person talking. So if I like, let's maybe talk after lecture if that's okay. Okay. All right. So, okay, so that's that. So one more thing about sorting. So I promised you something the other day, so I'll do it now. So let's say that you want to sort last names or something. So if you have last names, whatever, so I'll just so something like this. So one thing you can always do is, and that's what you would probably do, is you could say sorted of L, right? And that is going to be, like we just mentioned, O of n log n, where n is the length of L, because that's what Python's built-in sort does. So we'll talk about the exact algorithm later on. But let's say that you had this idea that I mentioned last time, where I'll just keep separate piles of last names starting with A and last names starting with B and last names starting with C, and I'll sort them separately. So sometimes that turns out to be useful. So, and this is what's called bucket sort. So what you can do is say, okay, so I'll have those buckets, and initially they're nothing. And then I'll go through the elements of the list. And I'll put the element in its corresponding bucket. So I'll say buckets at E at 0. So this would be the first letter of the string. And maybe it's empty, or maybe it's already there. So if it's empty, I need to just make it be the list that contains the element. That would be like this. And otherwise, what I'll do is I'll append the new element to the corresponding bucket. Right? So the idea is I start with buckets being just empty, and then it becomes the case that the first bucket is this. And then it becomes the case that the second bucket is, I'm not going to type it, so it's going to be this. And then if I need to add another one here, like this, that would be added here and so on. Okay. So that way I'll separate things out into the separate buckets. And the idea then is I'll go and sort the separate buckets separately. So what is Discord saying? So what's the assumption? So the assumption that we're, so the assumption is, so like we're not really making an assumption here, we're just kind of estimating. So this doesn't work with, like we mentioned, you're kind of like you are saying, and like I said, in the worst case, it's an infinite loop. So, okay. So what we're gonna do now, well, now we got to sort each separate bucket and then combine all of them together, right? So what we would do is we would say, okay, so all keys is the sorted version of the keys of buckets, like so. And then the result would be like this. And then I'll go through all the keys. So for K and all keys. And I'll extend the result with the sorted version of buckets at K. So the reason I go through the keys like this is because I first want to extend the buckets with everything that starts with A, and then with B, and then with C. I need the keys to be in a particular order. Okay, so just like with the other situation, what's the worst case complexity of this? Well, in the worst case, the buckets don't matter. In the worst case, everything starts with A. So all of that is pointless, if not counterproductive, because all you've done is you've created one big list that contains all of your data which you already had. Because you keep doing this. And then this one, you just do sorted on the one big bucket, which we said sorted is O of n log n. So now here, like we mentioned, accessing elements of a dictionary is constant time. So here, this entire thing is going to be, well, depends on how you think about append, but O of n, because you're building one big list that's, again, of length n. So this part is proportional to n because you're building a list of length n. And then this part is proportional to n log n because all you're doing is you're sorting one big list using sorted, which is O of n log n. So complexity is O of n log n. So here, like, why might this be useful? Well, it might be useful if you know that the buckets are all gonna be small. So if all the buckets are small, in some sense, that, and here it's really gonna depend on the details. But if all the buckets are small, . sorted might take less time. So informally, like if you happen to know that all the buckets are going to be very small, you can say, well, sorted is just going to take a very small amount of time. Most of the time is going to be, so you're still going to spend time sorting, because if all the buckets are small, then there is a lot of buckets, but the time is basically going to be proportional to the amount of buckets. So this is kind of analogous to counting sort before, right? So in counting sort, the idea was to basically have buckets that correspond to just each element, right? That's what counting sort is you have one bucket for counting zeros, one bucket for counting ones, one bucket for counting twos, and so on. And then there you didn't really need to do any work sorting them, because every bucket had all the same elements. So here, the idea is kind of analogous. In some situations, this can be useful. Again, in the worst case analysis kind of situation, you're going to say, well, it's not doing anything. But sometimes in practice, it's useful. So of course, in general, kind of saying that the runtime is proportional to n log n, even in the worst case, that's not saying everything, because it might very well be that, like, oh, this sort is O of n log n. Well, it's 1,000,000 times n log n. That's still a lot. Or it might be 0.0001 times n squared. So theoretically, this kind of framework doesn't account for those situations. Now, in practice, the coefficients are usually pretty reasonable. So it's a very rare situation where you have those huge, huge coefficients. Just doesn't really happen. Okay. Yes.
So are you iterating? Oh, E0. Oh, it's the first letter.
Yeah, E0 is the first letter, yes. So each bucket is like A or Z or whatever.
Oh, so that letter is not on the
That's right. That's right. All right. Okay. Yeah, I feel like 4:40 to 5 p.m. don't really work as a lecture. On Friday, I'll see you Monday. Bye. Yeah.
One thing that you listed all the
Yes.
I just didn't have time to review. So merge is the built-in one, right?
Well, so it's like a slightly different version, but basically.
Both L dot sort and sorted, it's the same.
Well, yeah. So they're not exact. So they're called gem sort and merge sort, but it's basically merge sort. Yeah.
Oh.
I was just wondering, as far as like in the bucket sort,
Yeah.
the L in the dictionary in buckets or whatever, doesn't that have a worst case time complexity L below N?
It does not, because membership in a dictionary, access to elements in a dictionary, those all constantly.
Because I just looked it up. So I was curious, and it said it had a worst case time complexity.
Well, again, kind of for
I was just wondering what the difference is.
no, so first of all, this
It's for dictionary.
yeah. So here's the thing. It's true.
Yeah.
However, in practice in this
Yeah.
analysis,
Okay.
people use O of n. The reason they use O of 1, sorry. The reason they use O of 1 is that, like, again, it's kind of like with the Bolded sort. It's gonna be the worst case is gonna be really rare.
Okay.
So this is unlike the worst case for something like bubble
Yeah.
sort, which is gonna happen basically all the time.
Yeah.
With a dictionary, the way it's implemented is
Is it happening?
that's right. Yeah. So in Python, it's a hash table.
Yeah.
It could also be kind of the binary search tree, or whatever.
Yeah.
And in both cases, like in practice, it's
Okay. That makes sense.
Yeah.
Okay.
Yeah.
Is there a reason we did not extend the not append?
Yeah. So 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 here we're making one flat list. And that means that we're kind of wanting to add this thing to the end of the list. So the difference is, right? So if you do L is, so if you do append, that's gonna look like this. Right, so here this might be a list,
Right,
and
okay.
we're kind of extending with them.
I see. Okay.
Yeah.
One more thing,
Yeah.
Yeah, so, for the end of the bogus sort, we did LILJ equals the other one.
Right.
We don't have to worry about deep copying it because they're tuples and they're getting unpacked, right? Is that the reason?
Well, no, that's not the reason.
Okay.
So what we're doing here essentially is we're saying put this number at location I in the list down.
Right.
So we're not really copying anything.
Okay.
So if it were the case that we're sorting stuff that's mutable rather than integers, you might worry, okay, like what are we doing here? So like if we're sorting something like this, right? And then you would say like L0, swap L0 and L1.
Right.
So it still would be fine, but there you would worry, okay, like, yeah, like what we're doing is we're not really moving this list 3-4.
Right.
We're just saying that L0 is now gonna have the address 3-4,
Right.
and L1 is gonna have the address of 1-2.
Right.
Here, those are integers anyways, so like, yes, technically, again, it would be the addresses that get swapped, but you cannot change the content of an integer.
Okay, so it just works. It's an
So,
integer, but
well, no, it would work for less.
Oh, it would work still.
Yeah, well, it's just that like what we're doing is we're just like moving the stuff around, right? So here, like both in this case and if it's integers, we're gonna say, okay, like L in the memory table used to be whatever at 1000 at 2000, where at 1000 at 2000 is the address of 1-2, the address of 3-4, and then it changes to this.
Right. Okay.
So so here, this would be a shallow copy if you were sorting this, which you can do by the way. Here, you're doing a shallow copy of integers, except it doesn't matter. It's like there's no deep copy of integers.
Okay.
But either way, it's fine because basically you have a list like this, whatever kind of object you have.
Right.
And what you're doing here is you're saying copy the address LHA to the address LFI.
Right.
And either way, you're rearranging this kind of thing,
Right.
which is what's one.
Okay, excellent.
Yeah.
Last thing, for the complexity, we said it's proportional to n factorial, but
Right.
that assumes that we're only getting a particular permutation once.
Yeah,
Statistically, it would be more than once, wouldn't it?
well, some more than once and some none at all.
So can we assume that, okay, right, so it averages up.
Well, I mean, like, technically, I think the most right thing to say is you would go, yeah, so like,
Okay.
like basically between like 0.5 and 1.5,
Okay.
which is all a constant factoring.
Right, okay, awesome, thank you very much. Have a good night.
Yeah, I was saying, you see the is sorted function.
Yeah.
It's prematurely returning true over here.
Yeah.
So if it's
Yeah.
sorted, if it's true here, it will already return.
Did I say, no, but like, it's, you swap that, so it's returning false, not true.
Oh, I swapped it. Oh, I read it
Yeah.
wrong. And one thing, next week we don't have a lab, right? So
You
what,
do,
so do
why
we
not?
go to the lab?
Why do you say you don't have a lot?
Wait, it wasn't the last lab this week?
No.
Oh, okay. Oh, see.
Yeah.
For bucket sorting, like, all numbers are 0 and 0, 0.
Yeah.
So do we have to make another bucket, like, if all these are going in one bucket?
Well, I mean, so like what I wrote only works with strings, right?
Let's say
So-
we have like 2 words, starts with
Yeah,
Eight
it's so you might have a situation where bucket sort is just not effective, like that happened. So in general, like you're right, that you might even have kind of buckets within buckets. That's like one possible design. There's like lots of possibilities there.
How about that? Let's see,